All right, calculus here with video number 2 in our series looking at solving or finding limits analytically. So in our first video, we looked at the difference between indeterminate and undefined. So again, indeterminate it's going to be our 0 over 0 or infinity over infinity. And when we have something like that, that's usually an indicator that we have some form of a removable discontinuity. We're going to then use some algebra techniques to kind of remove so that we can solve our limits through direct substitution. So this video here, we're going to look at doing some various techniques to help us get what the actual limit is through direct substitution. So let's go over to the whiteboard and let's look at some examples. Okay, so I have up here, we're going to go through 3 examples. And our first one is going to be this one here in the upper left corner. So we have the square root of 2 plus x minus the square root of 2 over x as x approaches 0. Now, if a function is continuous, that means that we can go ahead and solve through direct substitution. Meaning, if there is no gap or asymptote at the point which we are going to evaluate the limit at, then we can solve through direct substitution. So we could see here that if I were to directly substitute in 0, I would get square root of 2 minus square root of 2 over 0, which is our indeterminate form. Okay, so I cannot solve this limit through direct substitution right now. However, this indeterminate is hinting at me that there is something that can be removed. There's something that I could simplify here. And that's what we're going to do first. So one technique, and typically we like to do this when we see radicals, is to multiply by the conjugate. Okay, so this technique here is multiply by the conjugate. So what I really want to do is get rid of those radicals that are in the numerator. So I'm going to go ahead and multiply by the conjugate. So 2 plus x plus square root of 2. So remember, when you multiply by the conjugate, the top and the bottom get multiplied by the same thing. So I'm going to do that. So now, rewriting my limit expression, we always rewrite the whole limit. Don't just write the body of the limit, you need to write that front part as well. So I'm going to multiply the numerator, so that becomes 2 plus x, and then we have minus 2 divided by, and now in the bottom we have x times 2 plus x plus square root of 2. Okay, so now I'm going to go ahead and simplify. So now I can see, okay, the 2 and then that minus 2 will cancel. So that's going to leave me with, and again, I rewrite all of the limit, not just the body of the limit. So now I have this. And I can again simplify further because the x's will cancel. So now we have limit x approaches 0 of 1 over that. Now we have removed the discontinuity. We removed that part that was messing us up when we did try to plug in 0. Now if you plug in 0, we do get a definitive answer. We will get 1 over square root of 2 plus square root of 2, which is 1 over 2 square root of 2. And we can verify that because we could take our expression and graph it and see what it is approaching as we get closer to 0, and we will get this irrational number. We could also do it numerically. So all of the other techniques will still work, but this allows us to be able to get a more exact answer. Because if we were to try to do this by looking at a graph or doing it through a table of numbers, this would not have given us a nice answer. Like I would have, this is an irrational number. So if I were looking at, for example, a table of numbers, I would not have gone, oh yeah, this is approaching 1 over square root of 1 over 2 square root of 2, because that's an irrational number. It's different from the ones we saw in the previous chapter where it was approaching 5, or it was approaching a fractional value which we're aware of, like a 0.5 or a 0.25. This is where now solving things analytically will be able to give us a more exact answer. So that's multiplying by a conjugate. That's our first technique. All right, let's go down to the next example here. So again, I have here this limit expression. I try always first to see if I could do this via direct substitution. So am I going to get an indeterminate form if I just directly plug it in? So I'm going to go ahead and plug in my -3. So -3 squared would be 9 minus 3 minus 6. So I'm already seeing a 0 in the numerator, and then in the denominator, 3 squared, that'll be 9 minus 9. We got a 0. So again, we get an indeterminate form. So cannot solve this right now via direct substitution, but this is indicating to me something can be removed. So I'm seeing I got quadratics. So the technique that we had done in the last video is going to work here as well. So this is, we're going to attempt to factor the polynomial. Okay. So again, I'm going to rewrite my expression. So I'm going to start there. So the numerator I could factor. So this will be x minus 2 and x plus 3. Then in the denominator, this is a difference of squares. I could factor that. So this will be x minus 3, x plus 3. So now by factoring, I can remove that discontinuity that was causing the issue, leaving me with an expression that is going to be continuous where I am looking at the function using the limit. Okay. Now, what I want to point out is this part here is still a discontinuous function. There's an asymptote in this graph. It's happening at 3. But I'm not looking at 3. I'm approaching -3. So when we remove the discontinuity, we're not removing all discontinuities from the graph. We're removing the discontinuity that is causing the issue, which is we're looking at the graph around the area of -3, and where it was before, there was an issue at -3. There was a hole in the graph. We're going to take that out so that we can evaluate the limit analytically. There's still another issue, which is there's a big asymptote at 3. But I don't care about that because I'm not interested at looking at 3. I'm interested in looking is at -3. So now we're safe with this function. We can go ahead and plug in the value. So now we'll do that. So -3 minus 2, that's going to be a -5. And then we got -3 minus 3 or -6. So my answer would be 5/6. And again, we can verify that by looking at it graphically. We can verify it by doing a table. So all the other techniques will still work. So I keep mentioning that because I just don't want you to think this is it. I got to always do it this way. No, sometimes it might be very difficult, or you might forget, oh, I don't remember how to factor that polynomial, or I forgot that whole conjugate trick. Okay, then do it the other ways. They'll give you the answer just the same. Okay, so sometimes it'll be easier to do it one way versus another. Okay, so now for our last one, I'm going to look at this limit here. So as I said earlier, try first to substitute. So if I look at this function here, where is it discontinuous? Where do I have asymptotes or holes in the graph? So I see here, there's a hole at 4. If I were to plug in 4, I'm going to have a problem. But where are we evaluating the limit? Is that 2? Is 2 going to cause an issue? No. So even though it kind of looks like, I'm going to have to factor and I'm going to have to maybe multiply by the conjugate, we really don't have to do it with this problem. This function is continuous, no asymptotes, no holes, where we are intending to look at it, which is at 2. So I'm safe in this problem to directly substitute. So I'm going to plug in 2 and I get 2 plus 2. And then in the bottom I get 2 minus 4. So we're going to get square root of 4 over a negative 2. That gives me 2 over negative 2 for an answer of negative 1. So there are going to be some limit problems that by appearance, the function or the body of the limit might look like you need to do some sort of simplifying but again, we want to always check, let me directly substitute. Is it going to give me an issue? Is there an asymptote or a hole at where I'm intending to look at the limit? If there is, then we're going to see, do I get that indeterminate form? Then I'm going to start using some algebra to rewrite the expression. If I don't get that indeterminate form, then we're safe because it's continuous at that point. We can just solve it through direct substitution. All right. So that does it for these 3 examples. There are plenty other examples in the textbook. In my next video, I'm going to now start to look at the ones involving those trig identities. So sine of x over x, 1 minus cosine of x over x, and how we're going to use some trig identities in those. So another technique of how to solve those elements analytically.